Hi everyone. So, well, welcome to the live stream. So tonight, what I'm going to do is I'm going to do one question on elasticity, and there's some questions on elasticity on the assignment that's due tomorrow. They're pretty straightforward, but I thought I'd do one. Just to show you how it's done, and then I've got 5 others on fluid statics, and that'll be on the assignment, which will be due next week. Okay, so well, let's begin. So let's take a look here at the first question I have. Aluminum has an elastic modulus of 70 gigapascals. Okay, and a bar of aluminum has a rectangular cross-sectional area of 1.5 centimeters by 5 centimeters. 1.5 centimeters by 2.5 centimeters, and a length of 1.5 meters. Okay, so what you should be picturing is like it's kind of like rectangular cross-sectional area, but it's a meter and a half long. All right. And I ask how much force is required to stretch the bar by 1 millimeter. So we're not going to stretch it a lot, but it is a metal, aluminum, so it is going to require quite a bit of force. Now, I'll just say something before I jump in and answer the question. Here I'm saying that we're going to stretch it. And when you stretch, a stretch is well, for a stretch, you need the elastic modulus, okay, or the Young's modulus. That is E, all right. Normally on a question, I'll give you all 3 values. Like I'll give you the elastic modulus, the shear modulus, and the bulk modulus, and I'll expect you to decide which one of the 3 you need. And so I should remind you which is which. The elastic modulus, which is E, that's the one that's used when you're either squishing something, okay, compression, or when you're pulling it apart. Okay, stretching it, as in this case. Okay, that's E, the elastic modulus. The shear modulus is given the symbol G, and you use that one whenever you grab an object and you just you apply a force parallel, 2 forces parallel like that. Of course, you have to imagine kind of like an object in between my hands here. If I move the object like that, then it'll flop over one way or the other way. That's a shear. Okay, and then the bulk modulus is when you squeeze it in on all sides. Okay, but here I do say that we're going to stretch it, and I do give you the elastic modulus. All right, So how do you do this? Well, switch over to here, and what's the formula? The formula is this one right here. Okay. All right, so you can see it there. F divided by A, where F is the amount of force required. That's what I'm asking for, how much force is required. Okay. A is the cross-sectional area of the object that you're stretching or compressing. All right. That's got to equal, so F divided by A, all right, that's got to equal E, which is the elastic modulus, and there it is, 70 gigapascals for aluminum, multiplied by delta L. Delta L is how much you're going to deform the material, 1 millimeter, and L naught is the original length of the material before the deformation. In this case, 1.5 meters. Okay, so there's the formula. Now, if this were a shear, it would look exactly the same, except it would be, instead of E, it would be G. And if it were a bulk modulus, then, well, let me just write that formula very, very briefly, because it actually involves, so let me do it over here. I'll rub it off in a second because it's not appropriate. But it would be B for the bulk modulus. And in the case of the bulk modulus, it's actually the volumes that are changing. Whoops, there we go. Okay, like that. So notice that the bulk modulus is a little bit different because it's the pressure's coming in on all sides, so it's actually the volume that changes. Okay, so very similar formulas, but for the bulk modulus, as I said, it's volumes and not lengths. Okay, so all right, well, this is the formula we want, and like I said, these problems are fairly straightforward, but the problem is that you have to get the right units. Okay, and that's where all the mistakes are made. Well, I don't know about all the mistakes, but that's usually where the mistakes are made. Okay, so let's get those values ready, and I'm just going to cut and paste them from another. Right, like this. Okay, so you can take a look here, A is the cross-sectional area, okay? Now, the cross-sectional area, sometimes your object is, like the cross-section is circular, in which case you would use the formula pi r squared. In this case, it has a rectangular cross-sectional area. It means it's got a length and a width associated with it, and so the area is just the length times the width, okay? So the cross-sectional area was 1.5 centimeters by 2.5 centimeters, so A is going to be 1.5 centimeters times 2.5 centimeters. It's probably easiest to convert that to meters first. So 1.5 centimeters is 0.015 meters, and 2.5 centimeters is 0.025 meters, and multiply that out and you get this number, or if you want it in scientific notation, 3.75 times 10 to the negative 4 meters squared. Okay, great. We've got A. Remember, we're trying to find F. We've got A. What about E? Well, I tell you E is 70. Oh, that was silly. It's actually 60. I think it doesn't matter. Okay, I did the problem with 60, so let's just do it with 60. Okay, so yes, just a minor typo there. So E is 60 gigapascals. Okay, and when we plug into formulas, we want to convert everything to MKS. Reason being that you plug in the numbers in MKS, you're guaranteed to get MKS out. Okay, but gigapascals is not MKS. Pascals is MKS, and so you have to get rid of the giga there. But giga means billion. Okay, so remember kilo. You've seen that a lot. Kilo is 1,000, 10 to the 3. Mega, you haven't seen that as much, but it's it'll show up in this course more often than it did last semester. Mega is a million, 10 to the 6. Okay, and giga is billion, 10 to the 9. Okay, so 60 gigapascals is 60 times 10 to the 9 pascals. The delta L, that's how much it deformed. I said it was 1 millimeter, but convert that to meters, it's 0.001 meters, or 10 to the minus 3 meters. And the original length was 1.5 meters. Okay, so nothing much deeper than to plug into this, but I like rearranging it before I plug in. So isolate F because that's what we're trying to solve. So just basically multiply both sides by A, and you get the following. All right, you get the following. All right, so there's the formula. Rearranged. I basically just multiply both sides by A. There it is with all the numbers plugged into it. Okay, and that's going to give me 15,000, and the answer comes out in newtons. But I'm going to express that as 15 kilonewtons. Okay, because kilo is 1,000, so 15,000, 15 kilonewtons. All right, there you go. There's the answer. All right, so aluminum is pretty strong. And your bar is 1.5 meters long, but just to stretch it 1 millimeter, okay, with about the width of a dime, okay, that's going to require quite a bit of force because it is, after all, a metal. All right, nothing much deeper with these problems. So there we go. Let's do the next problem. So now we're going to switch to fluids. Okay, so how tall does the column of water of a barometer have to be if we want to use it to measure atmospheric pressure? Okay, so how tall does a column of water of a barometer have to be if we want to use it to measure atmospheric pressure? Now, in the pre-recorded lecture, I did mercury, which is usually what barometers are made out of. They're usually made out of mercury, and mercury has a much higher density than water. It's 13.6 grams per cubic centimeter. But here we're going to say, you know what? Can we make a barometer out of water? And and then if we did, how tall would that column have to be? With mercury, it turns out that the column has to be at least 760 millimeters, because that's how high one atmosphere would push it up. But how much does it have to be for water? Let me just remind you what a barometer looks like. Okay, so a barometer is basically, you have like a tub of fluid here. In this case, it's water. So you can see the blue dots there represent the water. And what you have is a like a test tube, but it's a really long test tube. Okay, so basically a tube which is closed at one end and open at the other end. Originally, the entire tube is filled with water. So you like lay it down in the tub and it's all filled with water. But then you lift it up, and when you lift it up, if the column is long enough, okay, what will happen is the water will actually break away from the closed end. It'll actually drop below it. And then of course what's up in here is a vacuum. Okay, it's like literally there's no air in there at all. All right, it's a vacuum because after all the whole tube was filled with fluid. So where would the air come from if there were air up there? So it's a vacuum. Okay, and but out here, you have 1 atmosphere of pressure. So outside of the tube out here is 1 atmosphere of pressure, and inside the tube here is a vacuum. What's actually happening is the atmospheric pressure is pushing down on the fluid here, and that's causing the fluid to go up, 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 up like that. Now, of course, the atmospheric pressure is only so strong. Okay, so there's only so much force per square meter, and so that's only going to be able to push the fluid up so far. Okay, with mercury, that H there, that height, is 760 millimeters if you've got 1 atmosphere. But the question is, how high would that column be if it's water? All right, so how do you solve that? Well, remember, when you go down into a fluid, the pressure increases. Okay, conversely, maybe I should just go back to that diagram. Okay, conversely, if you go up in a fluid, the pressure decreases. So the pressure right at this point here, okay, the right where that vacuum is, the pressure is 0. As you go down, the pressure increases until you get to that water line right here. And what's the pressure down here? 1 atmosphere. So this entire column here must be exerting 1 atmosphere of pressure. Okay, so is there a relationship between the height that or the depth, I guess we would say depth, inside of a fluid and how much pressure there is? There's a relationship like that, and it's basically P is equal to rho GH. Okay, and so let me just cut and paste that solution. It's pretty easy, but still want to go through it. Okay, and I also said let's be accurate to 6 significant figures. So I'm going to actually use a lot of digits here. Usually we only do 3 significant figures, but okay, so what's the pressure in a fluid if you go down a depth H? The pressure is given by rho GH. Okay, so there's that formula. Now the barometer is a little bit peculiar because the column is above the water line. Okay, but usually we talk about like diving down into a pool or something like that. But it's the same principle. As you start at where the vacuum is and you go down, the pressure increases. And how much pressure do you need by the time you get to the bottom? Well, you need 1 atmosphere of pressure. So P is equal to rho GH. P here, the pressure that you need, is 1 atmosphere. So that entire column from the vacuum down to the fluid line of the tub, okay, that has to equal 1 atmosphere of pressure. Well, 1 atmosphere, I actually looked it up on Wikipedia, is defined as 101.325 kilopascals. Okay, so that's a very accurate value for the atmospheric pressure. And then, of course, kilopascals is not MKS. We need that in pascals. So that's 101,325 pascals. Okay, so being very accurate there. The density of the fluid, well, it's water. The density of water is 1,000 kilograms per meter cubed by definition. Okay, so by definition, and so that's rho. G, we usually round off to 10 meters per second squared because we're not that interested in being super accurate. But here, again, I looked this up on Wikipedia. The acceleration due to gravity is 9.80665 meters per second squared. So very accurate number there. And the height, that's what we want to find. Okay, so I just took this formula here, rearranged it. H is equal to P divided by rho G, plugged in the numbers, and I found that it takes 10.3323 meters, like 10 meters and 33 centimeters, like 10 meters and a third. Okay, so that's quite high. Okay, that's like over 30 feet. All right, so that column there, let's switch back to this again. That column there, that whole height there, would be about 30 feet or 10 meters. Okay, if you wanted to make a barometer out of water. Not very practical. Okay, now here's something that's very counterintuitive. Like, how does a straw work? When we drink through a straw, what we do is we create a vacuum with our mouth, and we suck up the water through the vacuum, and eventually, fluid goes into our mouth. But what if we had a straw which was over 30 feet high, more than 10 meters, 10.33 meters. You know, you wouldn't be able to, no matter how hard you sucked on the straw, you wouldn't be able to draw the water up into it. And the reason is the best you could do, and you know, we just can't even produce a vacuum. But even if you could, even with your mouth, if you could, you know, inhale hard enough to actually produce a vacuum at the top of the straw, the best you could draw the water up would be only 10.33 meters. Okay, so you know, we don't usually experience that in day-to-day life, that you know, that if your straw is too long, you can't suck up the fluid through it. We don't experience that because, you know, it takes like 10 meters before you start to get to the point where, you know, you just can't pull the water up any further with a vacuum. Okay, but you know, if we did, if you know, like if you wanted to do this experiment, I guess you could do it with the garden hose. Go to the top of the building and just try to suck the water up through the garden hose, and you would see that you know, even if you could produce a perfect vacuum, and there's no way humans could, you could only suck the water up like 30 feet or something like that. You couldn't possibly pull the water up further than that. Okay, so there you go. This is a kind of a creative use of that formula. P is equal to rho GH. Another way is like in the assignment, I have some object which is submerged in mercury, I think 35 centimeters. And that's another way to think about it. So, you know, like back to this diagram here. So you have a fluid line here and you submerge an object. Here, I guess I could draw an object down here. Like, you know, you submerge an object like this inside of the fluid, and you say, okay, I've submerged at a distance h like this. And you ask yourself, okay, how much pressure is on that object now that it's been submerged the distance h under the fluid? Okay, so that also for that problem you would also use P is equal to rho GH. Okay, let me take a look at the chat here, see if there's any questions. Oh, we got 5 people on. All right, so I got some points here. So let me go back a little bit. Yeah, Dave, I did notice that the 60 versus 70. Let's take a look. The 17,500. Okay, so back to question number 1. Okay, so I'm going to back up just a little bit because I might have made a mistake. I don't know. So this one right here, I might have made a computational error. Let me see here. Let me just cut and paste this into my. Let me cut and paste that into my, I wonder if the error is because I switched 70 and 60. No, I'm getting that. Let me just see, what if I put 70 there? Yes, okay. So, at least, yeah, if you use 70 gigapascals, then yeah, it's 17,500 newtons. But with the 60, it's actually 15,000. Okay, yeah. Okay, actually, Dave, you did say that. All right. Okay, so it looks like that's been resolved. All right. Okay, let's move on. So we're up on question number 3 right now. Okay. So, by the way, there's a bit of a lag between the chat and you know, what I see at my end. So you know, I look over every once in a while, and what I'll do is I'll finish a problem and then I'll look to see if there's any questions and go back. So it may be a little bit before I actually answer one of your questions, but I'll eventually get to them. All right, see if everything is working fine. It is. Great. Okay, so question number 3. What is the buoyant force on an object with dimensions 3 centimeters by 4 centimeters by 5 centimeters submerged in water? It almost looks like there isn't enough information there, but there is. Okay, so what the buoyant force is basically, this is Archimedes, what Archimedes discovered. What the buoyant force is it's the force of an object when it's submerged under a fluid upwards. Okay, so the fluid wants to push an object upwards. Gravity wants to pull it down, and the fluid wants to push it upwards. Okay, so I'm not asking for the apparent weight or anything like that. I'm just asking for that upwards force. Okay, and it turns out that Archimedes discovered that the buoyant force FB is just the weight. Actually, I've got it written here. Let Let me just cut and paste my solution over here. So basically, the buoyant force is just the weight of the displaced fluid. Okay, so it's just the weight of the displaced fluid. Now, what does that mean? So you've got this object, and it doesn't matter what the object is. When you submerge it in the fluid, I mean, where the object is, there would have been fluid, and so whatever fluid is would have been where the object is, it got displaced, it got pushed aside. Okay, and so you could say, well, how much fluid got pushed aside? What does it weigh? Okay, and that weight is actually the buoyant force. All right, and so it's a weight. All right, so the buoyant force is a weight. Now, weight, don't confuse weight and mass. Remember from last semester, the mass is how much substance there is. The weight is the force of gravity. So it's basically the force of gravity on that displaced fluid. All right, and you calculate that by mg. All right, so the buoyant force is going to equal mg. But here you have to be very careful. That m is not the mass of the object. That m is the mass of the displaced water. In this case, the fluid is water. Okay, so we have to figure out how much water, what was the mass of that displaced water? Because how much water got displaced? Well, the mass of the water is basically going to equal whatever the density of water is, and we know that that's 1,000 kilograms per meter cubed, multiplied by the volume of the water that was displaced. But the volume of the water that was displaced is exactly the volume of the object. Okay, so the logic is a little bit convoluted here, but let's think of it this way. When you submerge the object, it has a certain volume. The volume of the object equals the volume of the displaced fluid by definition. I mean, that's what you mean by displaced fluid. If you take that volume and you multiply it by the density of water, that's going to give you the mass of the water by definition of what you mean by, displaced there, by definition of what you mean by density and volume. Okay, so that'll give you the mass of the displaced water. Okay, then you multiply that by g, and that'll give you the weight. Okay, so let's finish off the problem. Here, what's the volume? Well, the volume of the object was 3 by 4 by 5 centimeters, and so that's like 0.03, 0.04 times 0.05 in meters. Multiplying that all together, that's like 6 times 10 to the minus 5 meters cubed. Okay, so that's the volume of water that gets displaced, exactly equal to the volume of the object. Multiply that by the density of water, and the density of water is 1,000 kilograms per meter cubed in MKS, and that's going to give you that the mass of the displaced water is 0.06 kilograms or 60 grams. Okay, although we want to work in MKS. All right, so now we have the mass of the displaced water. Multiply that by g, which I'll just round off to 10. Okay, and that's going to give me 0.6 newtons. Okay, so that's what the buoyant force is. Now, I didn't tell you anything else about the object. You don't know what it's made out of, what its mass is, or anything like that. So you can't even tell if it's going to sink or if it's going to float or whatever. Okay, there's still gravity pulling down on it. But I just, in this question, I'm just asking for the force of the fluid upwards, that buoyant force, and it's exactly equal to this. That's what Archimedes discovered, you know, when he was, as the story goes, he was taking a bath, and he goes, I weigh less in the bath. And he realized, okay, well, since he weighs less in the bath, the water pushes up on objects when they're submerged in it, and that's how he was able to get the density of a crown, and discovered that it was more lead than gold, and so the story goes. Okay, let me take a look here if there's any questions. All right, looks good. All right, let's go on to number 4. So number 4 is computationally pretty easy, but you know, maybe a little bit conceptually demanding. Only 10% of ice floats above water. That's approximately right. It depends on whether you're talking fresh water or salt water or whatever. We'll work with fresh water, okay? So only about 10% of ice floats above water. What's the density of ice? Okay? And you say, well, how do you solve that? Well, so Archimedes' principle, making use of that buoyant force, actually can be used to calculate how much something floats, like what volume of it floats, and also can be used to calculate what the apparent weight of something that is submerged. Okay, so in this problem, we want to use it for the fraction of the volume which floats. Okay, so here's the formula. Actually, I'll just cut and paste the whole solution. It's not that long. Okay, so here's the formula for when an object floats. Okay, now when does an object float? When the density of the object is less than the density of the fluid. So let's take a look at each of the pieces in this formula. This is the density of the object. Okay, so rho O, and there's the density of the fluid, rho F. Okay, that fraction, that number has to be less than 1. Okay, now we won't need this for the to solve the problem, but just so you know that floating only occurs when the object has a smaller density than the fluid. So of course, if rho O is smaller than rho F, the numerator is smaller than the denominator, the fraction is less than 1. Okay, that makes sense because on the other side of the equation we have Vs divided by Vo. Vs is the volume of the object which is submerged. Okay, so some of the volume is submerged and some of the volume is above. Okay, so Vs is just the submerged volume, and Vo is the total volume of the object. Well, obviously the submerged volume must be less than the total volume. Okay, you can't submerge something and there's more, like you can't have something floating and there's more volume under it than there is entire volume. Okay, so the submerged volume always has to be less than 1. And in fact, what Archimedes applied to floating, Archimedes' principle applied to floating shows is that this is the case. And as you can see, both sides there have to be less than 1. You'd have a contradiction otherwise. All right, a little bit of an aside there, but what did I tell you? I told you that 10% is above the fluid line. That's not the submerged. Okay, so that's the above. So the submerged is actually 90%. If 10% is above, 90% is below. Now, I don't ever try to be tricky in problems, but just be aware of that. Like if I tell you how much is above, just remember that Vs is how much is below the fluid line. Okay, so 10% above, 90% below. So that means that this ratio here of the submerged volume to the total volume is 0.9. 90% as a decimal is 0.9. Okay, and the fluid, well, it's fresh water. Okay, and so rho F is going to be 1,000 kilograms per meter cubed. Okay, and so just take this formula. Let's rearrange it. So I'm going to rearrange it because we're solving for the density of the object, ice in this case. Okay, so basically multiply both sides by rho F, and oops, let me just scroll down a bit here. And so if you plug in here, all right, we plug in rho F is the fluid is water, that's 1,000. Vs over V naught we just determined was 0.9, and so you get 900. Okay, so the density of ice is 900 kilograms per meter cubed. Okay, so less than water, as you expect, because ice floats on water. Okay, by the way, ice is the only strange material, no, not only, but it's one of these rare materials where the solid form is actually less dense than the liquid form. Usually when you freeze something it becomes solid, the solid is more dense than the liquid. But water's strange this way. It has to do with the molecular structure. When the kind of V-shaped H2O molecules start to click together, they'll actually expand. They'll actually, they have to form a lattice. They'll actually form a lattice which is of less density than when they're water. And so ice will actually float on top of water. Okay, so there you go. All right. All right, let me see if there's any questions. All right. Okay, so number 5. An object has a mass of 25 grams. Okay, so this one, before I jump in, this is, so the previous one was Archimedes' principle applied to things that are floating. This one is Archimedes' principle applied to something that sinks, okay? And so here I say I have an object. Its true mass is 25 grams, okay? And we're going to submerge it in ethanol. Okay, so ethanol is the drinkable form of alcohol. Okay, so when we submerge it in the ethanol, it'll actually appear to have a mass of only 15 grams. All right, so we can actually use that information to get what the density of the object is. All right, and then I don't expect you to memorize densities except for water. You should know the density of water because it's actually part of the metric system. When they decided how big a gram was, they said, well, let's just take 1 cubic centimeter of water and that's what a gram is. So they had a length unit first, and then they used the length unit, a centimeter, to obtain a mass unit using water. So it is important to know the density of water is 1 gram per cubic centimeter, or 1,000 kilograms per cubic meter. And I'm not going to give you that on a test. You should know that. Okay. I know these tests are open book, but still, you really should have that memorized even for your other courses in the future. Okay. Ethanol, though, I mean, I'm not going to make you look it up during a test. I'll give it to you, and its density is 0.789 grams per cubic centimeter. Okay. So what did I give you in this problem? I gave you the true mass, 25 grams, the apparent mass, 15 grams. Like what does it appear to have? What's the mass that it appears to have when it's submerged in ethanol, and the density of the ethanol? And I want you to calculate the density of the object. Okay. By the way, you're going to do something like this in your next lab, okay, which is the lab on Archimedes principle. All right, there I think you're going to use a brass cylinder and water, okay, instead of in this case whatever this object is, and ethanol. All right, so how do we do that? Well, the first thing is there's a lot of ways. I wouldn't say a lot of ways. There's several ways in which you can write the formula for when an object is submerged. Okay, now this is the way I wrote it in the lecture. Okay, so let's go through the pieces of it. So this is when an object is submerged, it appears to have a mass MO prime. So MO stands for the mass of the object, and the little prime there means apparent. Okay, so that's what it appears to have when it's submerged, and that's the 15 grams. Okay, MO here, which you could see there and there, okay, MO is the actual mass of the object, okay. Rho O is the density of the object, and rho F is the density of the fluid. By the way, in this case, this value has to be, that ratio has to be bigger than 1, okay. Why? Because the object will only sink if its density is bigger than the density of the object, okay? And that makes sense because if you take a look at the other side, you have MO here and you have MO minus MO prime. Well, obviously the numerator is going to be bigger than the denominator, and so you get that both sides of the equation are bigger than 1, okay? Again, we don't need that to solve this problem, but it's good to remember. I mean, I could ask a question like this. I could say the density of the object is this, the density of the fluid is this. What will it do? Will it sink? Will it float? Will it submarine, where it's below the fluid line but neither going up or down? Okay, so and you would answer that question by comparing the density of the object to the density of the fluid. Okay, so let's solve. And let me just cut and paste that solution there. All right. So what are we going to substitute in? For the mass of the object, 25 grams. For the apparent mass of the object, okay, 15 grams. Okay, the density of the fluid, it's 0.789 grams per cubic centimeter. And in equation 1 here, we're trying to solve for the density of the object. That's what I asked for. So we're trying to solve for RO here. And so I'm just going to multiply both sides by rho F. All right, and that gives me this equation like that. All right, and then substituting in, I substitute in like that. All right, now you'll notice something. You'll notice I didn't convert to MKS before I substituted in. And generally speaking, it's always safest to convert to MKS, substitute in, and then you'll get the answer out in MKS, all right? But I didn't here, okay? If you don't, you can keep the units, and of course you'll get the right answer providing you crunch the units through. But for some equations, and I'll point out these equations when they occur. For some equations, the units will fall out no matter what units you use. So you take a look here, that what I have highlighted there, in the numerator you have 25 grams, in the denominator you have 25 minus 15 grams, or 10 grams, and so you have grams in the numerator, grams in the denominator. The grams will cancel out. Okay, and so when you're working with this equation, you say, well, should I convert my masses here to kilograms? Well, it's kind of a waste of time to do that, because if you take a look at that piece there, okay, if you work in grams, you're working with the numbers I have. If you work in kilograms, okay, then basically the number on top would be 1,000th. You divide by 1,000. The bottom number would also be divided by 1,000, and so you're dividing the top and bottom number by the same number, and it basically just falls out. Okay, so the units fall out. And in some equations like that, you say to yourself, well, why should I do this extra work of converting? The units are just going to fall out anyhow. We saw that last semester with I guess conservation of momentum. In conservation of momentum problems, you had like mass on one side and mass on the other side, and as long as you were using the same units of mass on both sides, they would just cancel out. Okay, it's the same kind of thing here. Okay, and so all right, let's continue. So we work this out, and it turns out that the density of the object is 1.9725, and that's too many digits. So what I'm going to do is, what I usually do is, we'll just stick to 3 significant figures. We'll just assume that for the purpose of the lecture, all my numbers are accurate to 3 significant figures. Okay. All right. So let's see if there's any questions on that. Okay, good. Looks like there's no problems. So the last one is on hydraulics. Okay, so we're just doing fluid statics this week. So hydraulics, and hydraulics. I guess I don't need to really draw a diagram for it, but basically, if you have a fluid inside of a container, all right, and you increase the pressure on one side of the container by a certain amount, then it'll increase the pressure everywhere within the container by the same amount. That's roughly what Pascal's principle says. Mathematically, though, it's this formula right here. And maybe I should just write down the formula, so I can refer to it as I go over the problem. Okay, so let's read the problem here. A tube with circular cross-sectional area narrows from 5 centimeters at one end to 1.5 centimeters radius at another end. Okay, and it's filled with an incompressible fluid. By the way, Pascal's principle only works with incompressible fluids. Okay, that is a fluid which, when you put pressure on it, it sustains the pressure, but it doesn't actually, its volume doesn't change. Okay, so it doesn't have a pressure dependent volume. Okay, so that's what an incompressible fluid means. And we apply a force of 15 newtons at the 5 centimeter end. What is the force at the 1.5 centimeter end? You know what? I think I will draw a diagram, I think it will help. Okay, so let me just switch to this and create a new whiteboard. All right, so here's the 5 centimeter end of the tube, and it narrows down like this, okay, to 1.5 centimeters here, like that. Okay, and it's filled with an incompressible fluid. Okay, all in here is an incompressible fluid. And right now I'm showing those two ends as open, but you can imagine that maybe what I have in there is like a piston, like this. It's not the best diagram, but okay. So this is like a solid piston like this, and I can push in on that piston like that. Okay, so I can apply a force F1 like that, and this piston here has an area A1. Okay, and then maybe at this end, just so the fluid doesn't flow out, maybe there's another piston here like this. Okay, like that. And of course, as I apply a force on this end, there's going to be a force on that end. So like if I didn't apply any force here, there would be no force on this end here. Okay, but if I do apply a F1 there, there'll be a force here, F2, And the only other thing that you need to know is what A2 is. Okay, so I hope that that's kind of clear. I know the diagram's not that good, but you know, like I need the pistons in there just so the fluid doesn't flow out. So I'm going to apply this force F1 to this one piston, and it's going to want to push the fluid in this way. Okay, the fluid doesn't have to move. Okay, and it just needs to like have this pressure here in this area there. Okay, and then it will result in pressure increase over here, and that pressure increase is going to be a force over the area of the piston, which is at this end like that. Okay, so let me switch back. All right, so there we go. Basically what Pascal's principle says is the pressure everywhere is increased the same. So I increase the pressure at the one end by F1 divided by A1, so the pressure at the other one has to be F2 divided by A2, okay? Like that, all right? So what do you know here? Well, I give you enough information to calculate the areas. And so one end is like 5 centimeters radius, and the other end is 1.5 centimeters radius, okay? And so let me just cut and paste. All right, so we have, well, let's get rid of that for now. So let's do the areas first. Okay, so we have A1, and the way you calculate the area of a circular cross section is pi r squared. Okay, if it's rectangular, like in my first problem, which was that aluminum bar, it's just length times width. So area is like length times width if it's rectangular. But if it's a circle, it's pi r squared. All right, now at A1, the radius is 5 centimeters or 0.05 meters. Okay, so there's pi 3.14 multiplied by r, which is 0.05 meters squared, and that turns out to be this number here. Okay, 0.00785 meters squared. Same thing at A2. A2 is going to be pi r squared, but it's a different r. Okay, and so r now is going to be 1.5 centimeters or 0.015 meters. Square it, multiply by pi, and you get that value. All right, 0.000765 meters squared. Okay, and now we'll just take this equation here, and we're solving for F2. Okay, we're solving for F2, and so what I'll do is I'll just multiply both sides by A2, and so that'll give me that F2 is equal to F1 times the ratio A2 divided, whoops, that's not right. So what do we have here? We should have A1 on the bottom here like that. That should be A1. There we go. Okay, so F2 is going to be F1 A2 divided by A1. Basically, we had F1 divided by A1, so there's the F1 divided by A1. But then I multiply both sides by A2, so there it is. And I guess I just put the A1 and the A2 together to show you that it's kind of like the ratio of the forces is the same as the ratio of the areas. Okay, and so if we take A2 divided by A1, the numbers above, okay, here, and multiply it by F1, and I told you that F1 was 15 newtons. All right, it's covered, but there it is, 15 newtons. All right, so 15 newtons multiplied by the ratio of the areas tells you that it's going to be 1.35 newtons. Okay, so there you go. That answers that problem. Let's just take a look at that diagram one more time. And what you're seeing is when F is big, A is big. If you decrease the area, we have a small area, you'll have a small, okay? And that's because it's the ratio, F over A, that is the same, okay? So it's F over A that's the same. So if you go from a large area here to a smaller area there, then you have to go from a large force to a small force, okay? It's not the forces of the areas that are the same. What is the same? Well, what's F divided by A? By definition, F divided by A is the pressure. So what you can say is that the pressure here, P, and the pressure there are the same, okay? But of course, if it's the same pressure over a smaller area, is obtained with a smaller force. Okay, and that's basically what hydraulics is all about. The example that I did in the pre-recorded lecture was I actually used a small amount of force being exerted over a small area to create a large force over a large area, and that's, I guess that's more properly how hydraulics works. That's how you're able to lift cars. Okay, so you're able to lift a car by, just exerting a small force on a fluid flowing through a small line, and that'll generate a large force over a large area. And that's the drum. I don't know if you've ever seen cars being lifted on one of those car lifts in a garage. There's a big drum under there, and that drum is being filled with the hydraulic fluid. And as the drum gets filled with the hydraulic fluid, it lifts the car. But it doesn't take a lot of force to pump the fluid in because of Pascal's principle. Okay, well that's it for tonight. Let me take a look here in the chat. All right, well, it just seems that the only questions I had was, my silly little mistake there of 70 versus 60 gigapascals. If there are no other questions, then we're done. So let me just ask, let me chat in here. Everyone okay? If so, we're done. All right, let's call it an evening then. All right, bye-bye, everyone.